Imagine a world where objects can be in two places at once, where you can't measure something without changing it, where particles can tunnel through barriers that by all classical rules should be impenetrable. Welcome to the wild and wacky world of quantum physics, where the rules of classical physics that we are accustomed to do not apply. First, let's grapple with the idea of wave-particle duality. Picture the ocean waves flowing and crashing, ebbing and flowing. Now imagine a grain of sand, solid and definite. Quantum physics tells us that particles like electrons and photons can behave like both the wave and the grain of sand, depending on how we observe them. This is beautifully demonstrated by the double-slit experiment, where particles create a wave-like interference pattern unless we observe them, at which point they behave like solid particles. Next, we delve into the quantization of energy. In the quantum realm, energy is not a continuous flow but comes in discrete packets, or quanta. Imagine a string of Christmas lights. Each bulb represents a quantum of energy. The energy of light, for instance, is made up of these individual bulbs or photons, which is why we see light in individual packets, not as a continuous stream. Now let's consider the uncertainty principle. Picture trying to catch a fast-moving butterfly with a net. The more precisely you know where the butterfly is, the less certain you are about how fast it's going, and vice versa. This principle, formulated by Werner Heisenberg, tells us that we cannot know both the exact position and momentum of a particle at the same time. Then there's quantum tunneling. Imagine a ball rolling up a hill. If the hill is too steep or the ball doesn't have enough energy, it won't make it over. But in the quantum world, particles can tunnel through barriers even when they shouldn't have the energy to do so. This is why tunnel diodes work. Electrons can tunnel through a thin barrier, allowing current to flow where classical physics would predict it should be blocked. Finally, we explore quantum entanglement. Picture a pair of dice. No matter how far apart they are, if one shows a 6, the other also shows a 6. This is a simplistic way to think about quantum entanglement, where the state of one particle is instantly connected to the state of another, no matter the distance. To summarize, quantum physics is a fascinating realm where particles can act as waves and particles. Energy comes in discrete packets. We cannot know both the position and momentum of a particle. Particles can tunnel through barriers and particles can be entangled. These strange phenomena challenge our understanding of the world and open up exciting possibilities for future technologies.